All right, we are on to chapter 9, and obviously this is, I guess it would be exam 3 stuff, yes? So in the last couple of chapters, we talked about equations, we talked about balancing equations, and we talked about grams to moles. So we're going to basically kind of put all those things together in this chapter, and we're going to talk about stoichiometry and doing really calculations from equations. And a couple important things when we do calculations from equations, which is we always want to make sure that the equation is balanced. So again, none of this will work out properly if it is not balanced. And again, we definitely will in this chapter use that molar mass conversion that we saw in the previous chapter, where we go from grams to moles and even moles back to grams. Again, that sort of molar mass from the periodic table is definitely the conversion factor that we're going to use a lot in this chapter to do these calculations. So in the previous chapter, when we talked about sort of just equations in general and how to balance equations, when we look at a balanced equation, we really can, as I mentioned then, and I think we saw the slide, we could look at the coefficients for the balanced equation, and they do represent some different things. We could say that there, again, is two molecules of H2 reacting with one molecule of O2 to give us two molecules of H2O. As I think I mentioned when we looked at the first time, this next relationship really is the relationship that we're going to use in this chapter and use most of the time when we sort of do these type of calculations. And that's sometimes referred to as the mole-to-mole relationship. And it also is, once again, just the coefficients from the balanced equation. So we can again say that we have 2 moles of H2 react with 1 mole of O2 and 2 moles of H2O. As we talked about at the end there, the last relationship that we definitely won't use pretty much at all in this chapter. But again, it's the conservation of mass sort of relationship. So we balance the equation. We have the same number of elements on each side, and they have the same molar masses on each side of the arrow. So we should end up with the same amount of reactants and products in terms of grams. But that mole-to-mole relationship definitely is what we will use a lot in this chapter. Now, the idea of sort of this process for these calculations, these are what are referred to as being stoichiometry or stoichiometry type calculations. And really, people get a little bit crazy in terms of stoichiometry or think it's super hard in a sense. But really, the idea here is stoichiometry is really just a conversion factor. And as we'll see here, unlike a sort of traditional conversion factor where maybe you find it in a table or look it up, thank you, where we actually get these conversion factors are from the balanced equation itself. And the reason we need to do that is if we have an equation, say like A plus B goes to C plus D, maybe we're given information about, how much of B we're starting with. And we want to know like how much of C we would produce, maybe how much of D would we produce. So if you have like one piece of information, how much reactants you're starting with, you can use stoichiometry in the calculation basically to figure out how much products you should produce. And we could actually do the other sort of calculation, which is if we know something about our products, like how much of one of our products we started with are sort of produced, we could actually figure out, how much of each of the reactants we started with. We also, as we'll talk about, can also figure out how much of, say, the other product we would produce if there was more than one product. So what stoichiometry allows you to do is use the balanced equation as a conversion factor. And again, if you just kind of know one piece of information, something about a reactant, something about a product, you basically can use the equation as a conversion factor and figure out everybody else that's in the equation, what's going on with how much is going to be produced. So very common questions that you're asked in sort of stoichiometry problems are, if you start out with a certain amount of reactants, how much products would you produce? Or vice versa, if you know how much products you produce, you could kind of go backwards and figure out how much of those reactants you actually started with to produce that much product. And this is all really based on sort of the mole to mole relationship that we see in that equation. Now, we are going to see in future chapters as well stoichiometry pop up in a number of places. When we talk about towards the end, we will see stoichiometry again. When we talk about gases, we will see stoichiometry again. So the units that you're associated with or may come across in stoichiometry problems can be a variety of units. You may be given moles, you may be given grams. I would say probably in this chapter, very commonly, grams and moles are the two that you're going to really commonly see in terms of units. When we get to gas chapter, we very much will see liters a lot of times. When we get to the solutions chapter, we'll see molarity, which is the concentration. So you will actually see a lot of different sort of units involved. We use, as I mentioned before, the mole method, which is, again, that mole to mole relationship that you get from the balance equation. And again, that's why it's so important always when you're doing anything with an equation to make sure it's balanced. Otherwise, it will throw your whole calculation off, especially when you're doing these type of problems. If you're starting with something that is not balanced, you definitely will kind of not get the right answer. So there are several steps to follow when you do stoichiometry problems, and you may not do all these steps here, but for basic stoichiometry problems, which is what we're going to talk about first, just basic stoichiometry problems, there's really kind of 4 steps to follow. There's an extra one on here, and the extra step on here is you can have a problem, again, when you're given everything just in words, and you're not actually given the equation, but you're given the equation in words. So if you do have that, the first thing you definitely want to do is make sure, as we maybe talked about, you just want to make sure you get all the correct formulas down. So remember, if you are given the equation in words, you want to get all the correct formulas down. And then you want to make sure once you have all the correct formulas down that you actually balance the equation. And that is the, kind of most important sort of step of this. Because again, if you don't start with that, everything else is going to be sort of flawed along the way. Next, pretty much whatever they give you, you want to get them to grams, and then you want to convert those grams to moles. And once again, you can be given units, all kinds of units. You could be given pounds, you could be feet, not feet, but pounds or grams, kilograms, things like that. But what units they sort of give you, you want to get them to grams, and then basically this step is take those grams to moles. Again, that is where the molar mass is going to come into play. Once you've done that, you're then going to actually do the stoichiometry step, which is the mole to mole relationship. You're going to go to the equation, you're going to find the mole to mole relationship, and you're going to use that. And the idea behind sort of this relationship is this. We oftentimes in these problems are given information about one thing in the equation, but we're actually interested in something else in the equation. And again, we need a conversion factor to allow us to go from one thing to the next. And it is the balance equation that allows us to do that. We use the calculated number of moles to convert to some other unit. So you really can, in a lot of cases, break this down into 4 steps. That if you just follow these sort of 4 steps in order, you oftentimes will end up at the right answer. 100% of the time, you want to make sure you have a balanced equation. If you're given the equation and there's numbers, you might want to take a good look at it, make sure it is balanced. If you see an equation, there's definitely no coefficients, you should take a pretty good look at it because it might not be balanced. You want to, again, as I mentioned, take whatever they give you and get them to grams and take those grams to moles. And again, that's the molar mass we're going to use to do that. Once again, the third step is really the stoichiometry step, which is you go to the equation and find the mole to mole relationship. And that's from the balanced equation. Now, what are the 2 things that you're interested in? Well, one of the things you're typically interested in is whatever information they gave you. So somebody in that equation, they're going to give you some information about. The other thing you're typically interested in is what you're looking to find. And those are kind of the 2 things you would want to go. And again, that mole to mole relationship is nothing more than just a coefficient that you use to balance the equation. So that is where that comes from. And then at the end here, you will usually take those moles and convert it into some other unit. A lot of times you may convert them into grams, which is like a very common sort of ending to these type of problems. And again, you would be using the molar mass at that point. But you could potentially be asked to solve for any type of unit at the end. But again, very commonly in this chapter, moles to grams at the end is a very common sort of ending. These are, again, your basic stoichiometry problems, 4 steps, balanced equation, grams to moles, mole to mole relationship, and mole to some other unit. Now, how do we get these relationships? Like I said, it all really starts from a balanced equation. And if you look at a balanced equation like the one we have here, there are several different sort of relationships that you could get from this equation. So from this particular equation, you could say, again, just looking at the coefficients, and obviously if there's nothing written there like normal in chemistry, the coefficient here is 1. We can get these stoichiometry relationships. We could say for every 2 moles of CO I throw in there, I will also need to toss in there 1 mole of O2. So that is basically a stoichiometric equality. I could also say for every 2 moles of CO I toss in there, I'm going to get out actually 2 moles of CO2. And again, these numbers are coming just from the coefficients from the equation. I can also say for every 1 mole of O2 that I toss in there, I will also get out 2 moles of CO2. These are all what are referred to as stoichiometric equalities. And these are really equalities like any other equality that we've seen before. 12 inches equals a foot, 453.6 grams is a pound. We could actually write conversion factors. Now, clearly, they are not equal to each other in terms of numbers. So 2 doesn't equal 1, obviously, and, in that type of situation. They are equal to each other in the sense of, in this particular reaction, that's sort of the proportion you need to toss in there for this reaction to take place. So just like if you were making cookies, you need so much flour, so much sugar, so much chocolate chips to toss in there to make a dozen cookies or 2 dozen cookies. This is the same idea here. These are the proportions of these things that you need to toss in there for this reaction to take place. So we do call these equalities. We do call these guys being equal to each other. But again, they're not equal to each other, obviously, in terms of numbers, but really proportions. And because these are really equalities that we could get from this one particular equation, and we could get 3 sort of relationships, we can write conversion factors for each of these. So for each of these, we could write 2 conversion factors just like normal. We could say for the first one there, we could have 2 moles of CO over 1 mole of O2, or we could flip it around like a normal conversion factor. 1 mole of O2 gives you 2 moles of CO. For the second one, we could say we have 2 moles of CO over 2 moles of CO2, or we could flip it around, 2 moles of CO2 up on top and 2 moles of CO on the bottom. And lastly, for the last one, we could say we have 1 mole of O2 over 2 moles of CO2, or 2 moles of CO2 gives us 1 mole of O2. So these are all the conversion factors that we could get from this one equation. So from this one balanced equation, we have 6 available conversion factors to use for us. Now, just like normal conversion factors, you definitely will not use them all in a problem. If you are, you're most likely doing something wrong if you try to use them all together. You're just going to pick the one that you need. So it just depends on the problem as to which one you need. But what these conversion factors allow us to do is, if I had information, say, about CO2, I could then maybe figure out something about CO because I have a conversion factor that allows me to go from one thing to the next. Any questions on that there? So to show you sort of how this sort of works here, let's just say, for example, here, I will do it there. Let's say that we produced in this case, and we'll do 25.0 grams of CO2. And we wanted to know how many grams of O2 did we start with. So we want to know basically how many grams of O2 did we start with in this case. So this is a basic stoichiometry problem, and essentially what makes it a basic stoichiometry problem, the way I would classify it, is we're just given one piece of information. And that's a typical sort of basic stoichiometry problem. You basically can only get to moles of one thing. And in this particular case, the only sort of information we have is the grams of CO2, and we could get the moles of it, but we can't get the moles of anything else. So that's typically how you know it's sort of a basic sort of problem. Whatever they give you, and a lot of times it's just one piece of information. You could only really get the moles of one thing. So we're going to follow our sort of 4 steps that we talked about here. So the first step obviously is done for us. We want to balance the equation. And it obviously is already balanced, so we don't have to do it in this case. The second step is basically we want to convert to moles. So basically we want to go from grams to moles. And in this particular case, there's only one piece of information given to us, which is we are produced here 25 grams of this guy, and we eventually want to figure out how many grams of O2 we started with. So the first thing we're going to do now is convert those grams into moles. And once again, it's a gram to mole conversion. So that is the molar mass. So I will need to go to the periodic table and get the molar mass of CO2. And again, that's 1 carbon at 12.01 plus 2 oxygens at 16. And that's going to give us 4401 grams per mole. So the molar mass here for CO2 is 4401. And that again is what we're going to use as our conversion factor here to do this step. So I'm going to take my 25 grams of CO2 that was given to us. And again, all I'm doing is just using the periodic table and getting the molar mass, which gave me 4401 grams on the bottom, moles on top. And if I do that here, 25 divided by 4401, that's going to give me 0.56805 moles of CO2. Now, at this particular point, I'm not going to round or anything like that because I'm definitely using that number to continue on. And in fact, you could just continue on without getting a number at this point, but I'm just going to take it to a few extra digits. So the reason I need to do this step after I balance the equation is if I look at my equation, and I zoom in to help, no, but would grab that. The only piece of information I have at this point is about CO2. But I'm really not interested in CO2. I am interested in O2. So what I need to do at this point is find a way to go from CO2 to O2. And this is really what the stoichiometry is all about. It's really just a conversion factor. And that's going to be our third step. And our third step is basically take the mole to mole relationship that we see there from the equation. So the mole to mole relationship from the equation. And as I just did, by looking at the balanced equation, that is going to give us our mole to mole relationship, which in this case is, as we saw earlier, a 1 mole of O2 gives us 2 moles of CO2. And that gives us an option here of these 2 conversion factors over here. We could either use this conversion factor or this conversion factor. And just like a normal conversion factor, the thing that we want to get rid of needs to end up in the opposite location. So if we think about where we are in the calculation, at this point I have 0.56805 moles of CO2. I want to get rid of the CO2. And this is going to be the stoichiometry part of it. So when I look at my option of conversion factors over here, the one that has CO2 on the bottom is going to be this very first one. And that's going to be the one that I want to use here. Again, just like a normal conversion factor, it puts the CO2 in the opposite location. So that is going to give me my 1 mole of O2 up on top and my 2 moles of CO2 on the bottom. And right there, that is the big stoichiometry move of the season, as just picking the right conversion factor from the actual balanced equation. Any questions on that? Obviously, when we do our normal sort of calculation here, our moles of CO2 are going to cancel. And now we are going to end up with moles of O2. And again, I'm not going to round at this point because I'm not really done with my calculation. And that's going to give us moles of O2. So really the whole purpose of these steps to do in these orders is it sets everything up correctly for you. You need the balanced equation to do step number 3. Before you could do step number 3, because we're using a mole-to-mole relationship, you have to get whatever units they gave you into moles, so everything cancels out correctly. Now, if by some chance the question wanted to know how many moles I needed, I would be done at this point. I could just round it to the proper number of sig figs and be done. But in this particular case, I do have to actually do the 4th step of my calculation, which is take the moles to whatever unit we're looking for. And in this particular case, we are looking for grams. So we will do the 4th step here, which is now convert my moles. And by the way, if you do this correctly, which hopefully you should, when you get to step number 4, you should always be in moles. So you should always be in units of moles at this point when you get to this step. If you're not in units of moles, you probably did maybe something wrong along the way. And again, we're going to use molar mass in this case to do it. The other thing that's really important to realize is we are no longer dealing with CO2, right? Because we've canceled it out. We are now dealing with O2. So in order to convert moles of O2 into grams of O2, we again need to go to the periodic table and get the molar mass of O2. So you don't want to use the same molar mass we used at the beginning because that was for CO2. Here we're at O2, and that's not too bad. O2 is basically 2 times 16. And that's 32, grams per mole. So the last part of my calculation, I'm just going to kind of continue right there. I have moles of O2 up on top. I'm going to do moles of O2 on the bottom so they cancel. A little 32 grams of O2 up on top there. Moles of O2 will cancel. And now we times it by 32. And we end up with something like 9.09 grams of O2 in this case. This, by the way, is how much O2 we would need to put in there. So what that number represents is if you did this reaction and you put in there 9.09 grams of O2, if everything went perfect in this reaction, nothing fell off the side, no side reactions, you should produce 25 grams of CO2 when this reaction is done. So that's basically telling us, how much we need to put in there to do it. In terms of significant figures, really everything's sort of exact in here. So in most cases, you are going to kind of look back at that very first number, which is 3 significant figures, and our answer would have 3 significant figures. Again, these are the 4 steps, as you can see, for stoichiometry that you want to follow, and it should get you there. Any questions on that there? Now, I personally here at this point kind of did it step by step, got an answer along the way, which for me is perfectly fine. Some instructors will want you to kind of do it all in one step, which you definitely can. If you are going to get answers after each step here, you definitely want to take it to a few extra digits until the end and kind of clean it up at the end. But you absolutely could do this calculation just straight on through. So you could have just went from basically here to here to here, basically, and just kind of did it all in one calculation without getting the numbers in between, and obviously setting it up like a dimensional analysis, top and bottom. So you do want to make sure you're setting this up, dimensional analysis, top, bottom. Let's talk about some common errors that people do when they're doing these type of problems. Common error number one, I would say, when they're using the molar mass, as we talked about with molar mass, they want to do it with the coefficient. And again, when you're calculating molar mass, the coefficient should not play into that. It should be based just on the formula. Because if you use the coefficient for your molar mass and then use the coefficient for the stoichiometry, you over coefficient, yeah, and you will get the wrong answer. And when you're asked to calculate the molar mass of something, again, it's per 1 mole, which means you need to use just the formula by itself. So again, in this case, I did not care there was a 2 in front of the CO2 when I did the molar mass. The molar mass comes from the periodic table, comes from the formula CO2, and that is how you calculate the molar mass. So you don't want to kind of incorporate the stoichiometry step with the molar mass step. That again is a super very common error. Second sort of thing that people sometimes misunderstand about stoichiometry is they think, for example, and maybe I'll come back to what I had here. I had that thing. So when they look at an equation and they're doing stoichiometry problems, a lot of times people have sort of the misunderstanding that you have to sort of do the relationship across the arrow. Like, hey, we have to go from here to here or from here to here. And you definitely could do that. So you could do relationships sort of across the arrow. But you could also stay on the same side of the arrow and do the same calculation. So if I knew something about B, but I was interested in A, I could do the exact same calculation and figure about A. Same thing over here on the product side. If you had a couple of products, if you knew something about C, you could use that relationship to figure out the other products. So you don't necessarily have to always go across the arrow to do stoichiometry relationships. You could do it between reactant and reactant. You could do it between product and product, or you could cross over the arrow and do the relationship between reactant and product. So again, you could do stoichiometry between anybody in the equation. Again, the balancing of the equation is the really important part to make sure you have the right mole-to-mole relationship. Any questions on that there? Yeah. All right. So this is sort of what we just talked about there. I'll just scroll it across. All right, so why don't you try one here? Lithium metal reacts with water to form hydrogen gas and lithium hydroxide. How many moles of hydrogen gas can you produce from 5.32 moles of lithium? Take a few moments. Again, go through the 4 steps and see what you come up with. Once again, they are balance an equation, convert to moles, mole to mole relationship from the equation, and moles to some other unit. All right, so take a few moments, see what you come up with here. Okay, so let's take a look at it and sort of see what we need to do. So the first thing here, we want to balance the equation. In this particular case, we do have everything in words. So as we were talking about earlier, we just want to make sure before we get to the balancing part that we do have the right formulas down. So lithium metal is just Li by itself, reacts with water, which hopefully H2O forms, which is an arrow. Hydrogen gas, which is H2, remember, not just H, but H2 is diatomic, and lithium hydroxide, lithium being +1, hydroxide being -1, gives us an LiOH. So once again, we just want to make sure before we even get to the balancing part that we have the proper formulas down, which we do in this case. Now we might want to get to the balancing part. Let's see here. Looks like maybe we need a 2 there, maybe a 2 there, maybe a 2 there. I'm just putting 2s down. How did I do? Let's see, 2 So we have 2 lithiums on each side. We got 4 hydrogens on the left. 2 and 2 is 4. 2 oxygens on the left, 2 on the right. That worked. 2 everybody up. So now we have our balanced equation at this point. So we'll check that off. Now, the next thing we want to look at really is sort of what was given to us. So in this particular case, we have 5.32 moles of lithium. And we're looking for how many moles of H2 is given to us. So the only piece of information given to us is lithium, and it's definitely in moles at this point. So there is no point in doing number 2 because it's already done for you. So a silly thing that sometimes people do is they unconvert a number just to reconvert it later. So if it's already done for you in these 4 steps, don't go backwards, just go forward. So we actually don't need to do step number 2 as it is already done for us. Once again, if it was not done for us, and maybe it was in grams, we would need to do step number 2 with the molar mass, but we don't need to in this case. At this point, we're now actually ready for the big stoichiometry step, and we want to go to the equation. And once again, the idea here is this. We are given information about this guy, but again, we're interested in this guy over here. So we need a way to kind of convert from one to the next, to go from here basically to here. And that is what the stoichiometry comes from. And we're going to do that. Once again, it is simply just the coefficient. And from the balanced equation for step number 3 here, I can see that for every 2 moles of lithium that I put in there, I will get out 1 mole of hydrogen. And once again, that is going to give us 2 options for a conversion factor. We could do 2 moles of lithium over 1 mole of hydrogen, or 1 mole of hydrogen over 2 moles of lithium. Once again, not going to use both of these. We're just going to use the one that we need. So starting with our moles that we have, 5.32 moles of lithium. Remember, we want to get rid of lithium, so we want lithium in the opposite location, which means we do want to use this conversion factor here. That's going to put the lithium on the bottom and put the hydrogen up on top, which is what we're looking for. And again, when I multiply and divide, the moles of lithium will cancel each other out. We'll take our 5.32 divided by 2, and we would end up with 2.66 moles of hydrogen. And that would take care of the stoichiometry step in this particular case. First off, any question on that there? Now, in this particular problem, the units that we're looking to end with are moles, which means, frankly, we don't need to do step number 4 in this case. We're actually done. We just need to put a box around it, and we are done at this point. This was actually not needed, and sometimes it's not needed. I will say in our class, probably a lot of times it is definitely needed, but sometimes it's not. So sometimes you may just be asked for moles, and you would be done with the calculation. But again, a lot of times you may have to continue on. So what this number represents is if you, in this particular reaction, put in there 5.32 moles of lithium, everything went perfect, no side reactions, you weren't a klutz and dropped everything all over the floor, you should produce in this reaction 2.66 moles of hydrogen. This is known as a theoretical yield. Now, a yield is always a product, yeah? So it's got to be a product if it's a yield, and that's be on the right-hand side of the arrow. That is why in the previous example that we calculated how much of a reactant, and that is not a yield, yeah? So that's why we wouldn't call what we calculated earlier in the previous example a yield. A yield has to be a product, and this is a theoretical yield. By the way, if I wanted my theoretical yield in grams, I would do step number 4, and I can convert it into grams and have it in grams in that case. So the theoretical yield is one of the things we'll talk about in this chapter. but it is, technically speaking, the perfect amount of product you should produce if nothing went haywire. Things always don't go perfect. So, but ideally, in theory, that's how much you should get. Any questions on that there? All right, let's try another one here using the same equation and reaction. So starting with the same reaction, but in this case, we want to know how many grams of H2 we would produce if we started with 81.75 grams of lithium. Some numbers that might be helpful here. Lithium is 6.942, I think, 43, I think, 41. 6.941. Hydrogen is 1.008. And we'll throw oxygen up there in case. There you go. All right, so once again here, follow those 4 steps. In this case, we're looking for grams. Balance the equation. Convert to moles. Okay, let's take a look. So again, we're given 81, we'll go here, 81.75 grams of lithium. And we want to eventually know, in this case, how many grams of water there is. So once again, this is a basic stoichiometry problem. And again, the way you can really recognize it is uh, based on the information given to you, you can pretty much only get to moles of one thing. So in this case, we have grams of lithium, which we definitely can get to moles to. We have no other information given to us. So it's going to be these 4 steps that we've been talking about. The good news is we did the last problem and we're using the same equation. So step number 1 is already done. We have the balance equation. Step number 2, in this case, we do need to do, because we're given information in grams, we need to get it to moles. And again, the purpose of why we need to get it to moles is for step number 3, which is a mole to mole relationship. So you got to get everybody in the right units. So to do that, we will need the molar mass from the periodic table here for lithium. So step number 2 here, we're going to take our 81.75 grams of lithium and convert it into moles. So we're going to go 81.75 grams of lithium. We're going to use the molar mass there of lithium, 6.941 grams on the bottom, moles on the top. And again, this comes from the periodic table. And again, if you want to get an answer at this point, you can. If you don't want to, you could actually just continue on with the calculation. And here I will put the answer up. And again, I'm not going to round too much here. 7778 moles of lithium. So we've now done basically our second step. Now we come to really the stoichiometry step of the process here. And again, the reason we need to do this is the only information we have is about lithium, but we're interested in hydrogen. So step number 3, going to the equation, using the coefficients from the balanced equation. Like we saw in the first part of this problem, for every 2 moles of lithium we put in there, we again get 1 mole of hydrogen out. And again, that gives you your option of 2 conversion factors to use. You can either use this one like so, or you could flip it around and put the hydrogen up on top and the lithium here on the bottom. Once again, here we're going to grab really the one that's going to work for us. So we do want to get rid of lithium, which is on top. So we will need lithium on the bottom, which is this conversion factor here on the right. And we're going to do 1 mole of hydrogen on top, which is going to get us the hydrogen, which is what we're looking for. And obviously here, the moles of lithium will cancel each other out. We're going to divide it by 2, basically, and we're going to end up with 5.8889 moles of hydrogen. So that takes care of step number 3. Any questions so far here? Now, in this particular problem, we are looking for grams at the end. So we do need to do step number 4, We do also need to again realize at this point we're no longer dealing with lithium. We have now done our stoichiometry, and now we are dealing with hydrogen. So in order to go from moles in this case back to grams of hydrogen, we will need the molar mass of hydrogen. So that is 2 times 1.008 from the periodic table, 2.016 grams per mole. So taking our number from above, our 5.8889 moles of hydrogen. Again, here we want the moles to cancel, so we're going to go a mole of hydrogen is 2.016 grams. Moles will cancel. And we will end up with about 11.87 grams of H2 in this case. Again, the 4 sig figs really off of the original number, as everything else sort of in between would probably be considered exact. This once again is a product, and this once again is a yield. And again, this is our theoretical yield in this case. In grams, by the way, over here is our theoretical yield in moles. So theoretical yields could be in any unit you want, but very commonly they are given in grams, actually. So once again, what this says is if you threw into this reaction 81.75 grams of lithium, everything went perfect, you in theory should get out 11.87 grams of hydrogen in this particular case. Once again, like I said before, if you do not want to get the answers in between, your calculation is set up would go from here to here to here, basically. Perfectly fine. And you don't have to get the answer in between if you don't want to. But if it helps you kind of break it up by parts, then definitely follow the steps that way. Any questions? Okay. Let's try another one here, maybe. That was the one we just did. All right, so based on this equation here, if we have 765 grams of C6H12O6 consumed, what is the mass of CO2 produced? So for mass, we're looking for grams here. I'm still highlighting, apparently. There you go. Let's try that again without the highlighter. There you go. So in this case, we want to know how many grams of CO2 produced. Again, some numbers to be helpful from the periodic table. 12.01 for carbon, hydrogen 1.008, and oxygen still 16, has not changed yet. But maybe soon. And again, still same 4 steps. Okay, let's take a look. So in this case, we have, again, a stoichiometry problem here. We are given 765 grams of this guy, and we're looking for how many grams of this one. So we're going to follow our steps here as, again, we really only have one piece of information given to us that we could get to moles. We have the balanced equation. I'm going to hope it's balanced. There's numbers in it, so I'm going to go with that. That does mean the next thing we need to do is convert into moles. And once again, this is the only piece of information we have to convert into moles. We'll have to go to our periodic table there and calculate the molar mass of this guy. So that's going to be 6 carbons at 12.01 each, plus 12 hydrogens, 1.008 each from the periodic table, and 6 oxygens at 16 grams per mole each. That's going to get us something there. About 180.2, it looks like, maybe. About 180.2 grams per mole would be our molar mass for our C6H12O6. Again, we're going to use that really to convert into moles. So we'll take our 765 grams of C6H12O6. Again, that's up on top. So to the bottom, we want grams. So we're going to take 180.2 grams on the bottom, moles of C6H12O6. In this particular example, I'm not going to actually get an answer. I'm just going to do it all in one calculation so you can see it. So this is basically step number 2 here. And again, if I stop right at this point, the grams will cancel, and I'm in moles of C6H12O6. Once again, we can now go to step number 3, which will be our mole-to-mole relationship. So in this particular case, once again, we want to look at the two things we're interested in. One thing is what they gave us. The other thing is what we're looking for. So again, from the equation where we always get this relationship from, we can see that for every 1 mole of C6H12O6, that gives us 6 moles of CO2. Again, that is what we could use for our conversion factor. So again, setting this up with dimensional analysis, we have moles of C6H12O6 on top. We want to get rid of it, so we're going to go opposite location here, 1 mole of that. And up on top is what we want, which is our 6 moles of CO2. This is going to be step number 3, as the moles of the C6H12O6 is going to cancel. Once again, if I stopped right at this point, I'm in units of moles of CO2, which in this case, we don't want moles of CO2. We do want to go to grams. So we do need to do, now that we did step number 3, we do need to do step number 4, which is take moles into grams. Once again, we do want to realize at this point that we are now at CO2 and not our original guy. So we do have to go back to the periodic table, and for CO2, again, calculate the molar mass. That's going to give us 12.01 for our carbon and 2 times 16 there for our oxygen. And that's going to give us what we saw, I think, in the previous problem there, 4401 grams per mole as the molar mass of CO2. That is what we're going to use for our 4th and final step here, which is, again, to get rid of moles of CO2, which are on top. So our moles of CO2 will go on the bottom. Our 4401 grams will go up on top. The moles of CO2 cancel, and this is step number 4 at this point. So as I was mentioning before, you could definitely just do it all in one calculation if you want. If you're more comfortable getting an answer after each step, get an answer at each step. It doesn't matter. Here we're just going to multiply everything on top. So we're going to go 765 times 6 times 4401, hit equals, divided by 180.2. And we're going to end up with approximately 1,121 grams of CO2. Again, in terms of significant figures, if we come back to this number, as everything else here would be considered probably exact, we really do want 3 sig figs, so that might get you to an 1120, no decimal point, grams of CO2. This, once again, would be a theoretical yield. And once again, a yield has to be a product, yeah? So it's got to be a product, which it is in this particular case. So just like the other calculations, in theory, if we put in there 765 grams of our C6H12O6, we should get out about 1,120 grams of CO2 if everything went perfect. And again, hopefully you can start seeing a pattern. It is just those 4 steps, followed in order, something done for you, go forward, don't go backwards. And again, it should lead you to the right answer at the end. Continue on here. First off, any questions on basic stoichiometry problems? Again, like I said, pretty much you want to follow those 4 steps, and I'll get you through it. Again, you could recognize, as I mentioned, it's a basic sort of problem where you're usually only given one piece of information, either about a reactant, about a product. You basically could just get the moles of one thing. We're going to skip that last example. We're going to continue on now, talk about maybe a little bit more complicated sort of stoichiometry problem that you come across, and sort of how to tackle those. And the idea behind this type of stoichiometry problem is these are what are sometimes referred to as limiting reagent problems. Some people call them limiting reactant problems, same idea. And the idea here is when you do a actual sort of reaction, the sort of relationship between the two reactants are one where there's usually a reactant that gets used up first or a reagent that gets used up first, and that is what is known as the limiting reagent. So in a stoichiometric sort of reaction, a lot of times there is what's known as the limiting reagent or reactant, same thing. And that's the one that gets used up first in the reaction. There's also a reagent that's referred to, as we'll talk about, as the excess reagent. And that one you have plenty of, and you actually have some of this left over when the reaction is done. So we have the limiting reagent that gets used up first in the chemical reaction. We have the excess reagent or reactant that's still there when the reaction's over with. You have plenty of it. You basically have leftovers of it when it's all said and done. Now, why is this really important when we talk about reactions and we talk about sort of using equations to figure out how much product we produce? The reason is very simple. If you just take a very simple sort of reaction where you take A plus B and it makes A and B, and let's just say, for example, that A in this case was our limiting reagent, and we'll just say B was our excess reagent. Now, because in this particular case, A is our limiting reagent, that means at some point, as we're making our product, which is A and B together, we are going to use up all of our A. And that's a really important sort of aspect of this, because if I need to make my product in this very simple reaction where I need one A and one B to come together, and I no longer have A, then there is no possible way you can make any more product. So the importance of the limiting reagent is it is always the limiting reagent that determines how much product you can form or produce, because as soon as it gets used up, there's no possible way you can make any more product. Again, in this example here, as soon as I run out of A, there's no way to put A and B together if I have no more A's, and I'm not going to be able to make product. So the limiting reagent is the important one. It tells you how much product you can make. Doesn't really tell you. It determines is a better way of saying that, right? It determines how much product you basically can make. So when we have a limiting reagent problem, it is still really a stoichiometry problem, but there is this additional sort of work, if you will, that you have to do to determine which one's your limiting reagent in order to do that. As I mentioned before, there's also the excess reagent, which you have plenty of, and you'll have some left over when the reaction is done. Ideally, your limiting reagent will be zero when the reaction's over, because again, it all should be used up, but you will have some of your excess reagent still present. So if we take a look at sort of this example here, we have some uh, female workout people and some male workout people, and we want to make workout buddies. We need one of each. So if I take one guy and one girl, we get one. If I take one guy and one girl, we get two. Take another guy and another girl, we get three. At this point, there is no more products being made, as I have run out here of our guys. And because of that, this is going to be, in this example, my limiting reagent. And as you can see, we still have some excess reagent left over. And we could even, as I mentioned before, figure out in this very simple example how much excess we have left over. In this case, we have two left over at the end of this reaction. So these are very common questions that you're sometimes asked, which is, how much product you're going to produce. And also with that, and we'll go over some of the calculations here in just a second, but you're very commonly asked, how much of that excess reagent you'll have left over as well. So that again is a very common way. So when we do these type of problems, these are limiting reagent problems. And the idea here is this, to be truthfully honest with you, there are multiple ways you could do these problems. There's at least three that I could very easily think of ways that you could actually do these problems. So I'm going to talk about two ways of doing it. And I won't leave the third one off the table because that's probably the best way of doing it, but they probably will yell at me if I teach you this early. So we will do these two ways here, and you can really choose sort of whichever way you want to do it. The second way I'm going to show you is probably how the book will kind of show you to do it, so you can see it kind of both ways. But the first way, or better yet, before we start talking about that, the way that we kind of know, for example, that we are in a limiting reagent situation is you have enough information, so you have enough info to calculate the moles of each reactant. So if you come across a problem that looks like a stoichiometry problem, and they give you enough information about both reactants that you could very easily get that information and convert them into moles, it definitely is a limiting reagent problem. Now, if you think about the problems that we did previously, we pretty much were only given like one piece of information. So we were only given like one reactant information. There was no way to calculate the moles of the other. So those are basic stoichiometry problems. But if you come across a problem where you could definitely get to the moles of each reactant, that is the biggest tell of it is a limiting reagent problem. And by the way, when you determine what is your limiting reagent, it actually has to be based on a calculation, not just a very, very common error that people make. They think it's always the smallest number that you're starting with, like the smallest amount of a reactant you're starting with. And that's not always the case. So the first method is this that we'll talk about predominantly here, and then we'll talk about the other method at the end and kind of show you the difference. But the method here really just follows the same four steps that we did previously. So if you remember the same four steps for our basic stoichiometry problem, we are still going to balance the equation, pretty much a standard no matter what method you choose. We are still going to convert whatever they gave us to moles, also pretty standard no matter what method you use. Right around here in this method, after we convert everybody into moles, we're actually going to determine our limiting reagent. So we're going to determine through a calculation which reactant is our limiting reagent. Once we do that, remember that it is the limiting reagent that determines how much product you're going to make. So at that point, we're going to use our limiting reagent to do our mole to mole relationship like we've done before. And then we're going to convert those moles into whatever units, we're looking for in that case. So this first method really follows the same method we've been using, except in between step number 2 and step number 3, you do have to do a very small calculation to figure out which one's your limiting reagent. Other than that, then you can proceed with the limiting reagent after that point. So let's take a look at sort of how we would go about doing that. And let's just say, for example, here, we started with 128 grams of sulfur and 760 grams of F2 in this particular reaction. And let's say we wanted to know how many grams of SF6. So this is a problem. We're given both pieces of that information. And the first thing I should recognize, obviously, is the stoichiometry problem here. And again, the first thing that I should recognize after that is they gave me grams of sulfur and they gave me grams of F2 in this case. That is basically information that will allow me to calculate the moles of each reactant. So because I could calculate the moles of each reactant, I automatically know that this is a limiting reagent problem, and I do need to, at some point, figure out which one's my limiting reagent. So that is sort of the key when you look at a problem. Like, okay, I got both reactants, I got grams of both, I definitely could get moles of each. That definitely is a limiting reagent problem. So how am I going to start this problem? Well, frankly, I'm just going to kind of follow, like I said, our steps we've been doing. I'm going to balance the equation, which was already done for me, so I don't have to do too much. In this particular case, I do need to convert both of these values into moles. So just like we did before, we're going to use the molar mass to do that. So again, sulfur on the periodic table, 3207. 3207. And fluorine is 19. So step number 2, we're going to convert to moles, just like we've done before. And we're going to convert both of those guys into moles. So for my sulfur, I'll take 128 grams of sulfur. I'm going to use the molar mass of sulfur, which is 3207 grams per mole. And that's going to give me my moles of sulfur here, 128 divided by 3207. And we're going to get 3.99, and we'll go one more, moles of sulfur. I'm going to do the exact same calculation for the F2. That is 760 grams of F2. Once again, using the molar mass from the periodic table, 2 times 19 in this case, because there's 2 fluorines, equals 38 grams per mole. So we'll use our 38 grams per mole here of F2, and we will end up with a nice round number, I think, 20 moles of F2. So first off, and like I said, no matter what method you choose, pretty much these are the same 2 steps you always follow. Balance the equation, convert to moles. Now, in this method, what you really want to kind of think about is these 2 numbers here are basically like our starting amounts of each of these reactants. So this is how much of each of these reactants we're going to actually put into this reaction to do it. Now, because I know this is a limiting reagent problem, as I mentioned a second ago, we are now balanced the equation. We convert it to moles. I now need to actually do the calculation to figure out which one is my limiting reagent. So how do we go about doing that calculation? Well, to figure out the limiting reagent, which is kind of what we want to figure out at this point, you can choose either one of the reactants. It does not matter which one you want to choose. And basically what you're going to do is you're going to pick either the sulfur in this case, or you're going to pick the F2 in this case. And basically what you're going to do is a very simple stoichiometry calculation between S and F2 in this case. And you want to know is, for example, let's say I choose the S. I want to know in this case how much F2 is needed to use up all the sulfur. So if I want to use up all my 3.99 moles of sulfur, I want to know how much F2 I need to put in there. So again, this is just a very simple stoichiometry problem. And to do that, I would go 3.991 moles of sulfur. I would go to my balanced equation and find the relationship between the sulfur and the fluorine. And from the coefficients, we can see it's a 1-to-3 relationship, right? So again, for every 1 mole of sulfur, I have 3 moles of fluorine. I'm going to use that as a calculation. So 1 mole of sulfur, 3 moles of fluorine. The moles of sulfur will cancel. And that will tell me at this point here, 3.991 times 3, that 11.97 moles of F2 is needed. So that number that I just calculated is, in theory, how much F2 you would have to put into this reaction to use up all of your sulfur. First off, any question on that calculation? Now, once I figure out how much F2 is needed, what do I do with that number? I'm going to compare it to how much F2 I have to start with, and that is above it. So in this case, I just calculated I need 11.97 moles of F2. If I come up here, I could see I have how many moles of F2 to begin with? I have 20 moles of F2. I need 11.9 moles. I got 20 moles. I have enough. And because I have enough, that tells me basically everything I need to know about this problem. It tells me I have enough F2. That means that F2 is my excess reagent. And by default, that will tell me that the sulfur is my limiting reagent. So even though I figured out which one was my excess reagent, the opposite guy is going to be my limiting in this case. Now, first off, any questions on that? So that is, again, the whole point of that little calculation is for you to compare how many moles of your starting you have and see if you have enough. Now, if I did this and I did not have enough, that would mean that that guy would be my limiting reagent and the other guy would be my excess reagent. Any questions on that? Now, I told you a second ago that you could choose either reactant, and that is true. And I'm going to show you the calculation for the other reactant. You do not need to do both of these calculations just to show you it works for either one. So let's just say I wanted to do it the other calculation, which is I want to know how much sulfur is needed to use up all my fluorine. So in this example, I would start with the starting amount of my fluorine, which is 20 moles. I will use the same relationship from the equation up here. And again, we're going to go with, in this case, 3 moles of fluorine on the bottom and 1 mole of sulfur up on top. The moles of fluorine will cancel. I'll take my 20 divided by 3. I will end up with 6.67 moles of sulfur is needed. So if I chose the other reagent, did the other calculation, what I just calculated was I need 6.67 moles of sulfur. If I come up to how much I started with, I'm a little short. I only got about 4 moles, right? So I do not have enough in this case. And that tells me the exact same thing the first calculation told me. I don't have enough of my sulfur, which means the sulfur is the limiting reagent. And I mean by default, the F2 would be the excess reagent. So again, you don't typically have to do both of these calculations, but it just wanted to show that you can choose either reactant. It doesn't matter which one you choose. You're just basically trying to figure out whichever reactant you choose, how much of the other one you need to put in there with it, and to see if you have enough. Any questions on that? Once I have done that and I have figured out my limiting reagent, now I basically can just roll back to my basic stoichiometry steps. So now that I figured it out that the sulfur here is my limiting reagent, I'm going to now do the actual problem, which is how much product I'm going to produce. So step number 3 is using my limiting reagent. And we want to make sure that we are also using the starting amount of our limiting reagent. So nothing to do with these calculations at this point, whichever one you chose. You probably don't have to do too much with those calculations other than use those to figure out your limiting reagent. You now want to go back to your limiting reagent and our starting amount, which is my 3.991 moles of sulfur, which is my limiting reagent. I am now going to do my mole-to-mole relationship between my limiting reagent, which is sulfur, and my product, which this one doesn't look too bad. It is a 1 mole of sulfur gives me 1 mole of SF6. So it's a 1-to-1 relationship. That means that I will produce, in this case, 3.991 moles of SF6. This would be my theoretical yield in moles, right? And at this point, we can then convert our moles into grams using the molar mass of SF6. And if I do that, my SF6 is 3207 plus 6 times 19. It's about 146.1. This guy's about 146.1 grams per mole from the periodic table if you calculate it. And I'm going to do my fourth step, which is convert my moles into grams. I'm going to go 146.1 grams per mole of SF6 from the periodic table. And that's going to get me here. Looks like about 583 grams of SF6 would be produced. That once again would be our theoretical yield in this case. So this method here is basically the same 4 steps that we did previously, with the insertion of the calculation to figure out your limiting reagent halfway through it, basically, is what you do. Any questions on those steps there? Now, one of the benefits of maybe doing this method versus the next one I'm going to show you is for the question that you're sometimes asked, which is how much of the limiting reagent, how much of the excess reagent is left over. So let's just say in this particular problem, we wanted to know how much of our excess is left over. So we could do that because we actually did the calculation we need when we were trying to determine our limiting reagent. We figured out here that the F2 was our excess reagent. And from this calculation we did earlier to figure out our limiting reagent, we figured out how much F2 we need to use. So we know how much F2 we started with. So if I take 20 moles, which is what I started with, and use the calculation I did earlier, which told me I need about 11.97 moles of it to use up my limiting reagent, that will tell me that at the end of this reaction, I will have approximately 8.03 moles of F2 left over, which if I wanted to know how many grams that is, I can multiply that by the molar mass of F2, which would give me 8.03 moles times my molar mass of 38 grams per mole. And we will go with about, go up on top so you can see it, 305 grams of F2 left over. So remember, in this reaction, we started with 760 grams of F2. We would have about 305 grams of it left over at the end of this reaction. And again, so we used about 400 or so, 450 some odd grams of it in this reaction. Again, for your limiting reagent, you should have about 0 left over, right? Because it's the one that's going to get completely used up. So you should have none of it left over. First off, any question on any part of that calculation there? Okay. So let me just show you sort of the other method that's very commonly used in these type of problems. And where do I want to show you that? Maybe I'll show you that here. All right, so 128 and 760, right? Yep. All right, so we have 128 grams and 760 grams of F2. And again, we want to know in this case how much SF6 we would produce. So here's really the other method, which is very popular these days. in all kinds of books. And basically what you do here is you follow the 4 steps that we've done previously, and you basically just do 2 separate calculations. So you take each reactant and you figure out how much product would each reactant basically produce. So you just simply do the 4 steps for each reactant separately and just figure out how much each produce. So what I would do in this case is I would take my 128 grams of sulfur. I would do my second step, right, which is convert to moles. So 3207 grams per mole of sulfur. The grams would cancel. I would then do my mole to mole relationship once again from the equation, which when we write that S and 3F, we got, right? So we have S plus 3F2 goes to SF6. I would now do my relationship between my first reactant and my product, which is a 1 mole of sulfur is 1 mole of SF6. Again, the moles of sulfur cancel. And at this point, I would use the molar mass of SF6, which we borrowed from the previous one, which I think was 146.1. So we'll use that, 146.1 grams per mole of SF6. And this obviously would be step number 3 and step number 4. Step number 1 would be our balance equation. And we would do this for sulfur. And we would see from sulfur, we would produce about 583 grams of SF6. We would then go back and take our second reactant and do a similar calculation from our second reactant using the molar mass, 38 grams per mole of F2, step number 2. Again, grams will cancel. We will now do our mole to mole relationship between F2 and our product. And that is a 3 mole of F2 to 1 mole of SF6. Again, the moles of F2 would cancel. That's our third step. And lastly, our fourth step, 146.1 grams of SF6 per mole of SF6. The moles will cancel, leaves us with grams. And we will see that the F2 will produce, in this case, about, I think I missed a 3 as well there. About 974 grams of SF6. So this is the other method where you basically just do 2 separate stoichiometry calculations, one from each reactant to the product of interest. And what you're looking for at the end here is the one that produced the smallest. So this one is the smallest product produced. And the one with the smallest product produced is your theoretical yield and your limiting reagent. Yeah. And basically for the second calculation, you just kind of wasted your time and you just don't use it for anything. You just scratch it out basically, and that would give you your product. So that is the other sort of very common method. Now, perhaps the downfall of this method is if you are asked that question about the excess reagent, you got to go back and do the calculation we just did in the previous one to figure out how much excess is left over. So you will have to kind of go back and kind of do that excess calculation anyways. So again, it's your choice, whichever way you want to do it. You like doing it, you can. But again, if you were going to do that excess calculation, you would have to actually go back and do this calculation to figure out how much of your excess you have left over. So you kind of have to go back and do that calculation anyways. So one of the nice things about the other method is sometimes you get really lucky. If you have to answer that question, you kind of already have the calculation done for you. You don't have to necessarily go back and do it. But you may not always be asked that question. So some people like to kind of do this method. And these are 2 different ways you could do this. Like I said, there's other ways you could do it as well. But we won't get into all the other ways. Any questions on that there? And by the way, on our other method, this number down here that we got, you can see it's the exact same number we got on the other method. That, again, is our theoretical yield on this calculation, obviously, as well. All right. So that's the key with limiting reagents. You recognize it by You have enough information to get to moles of each reactant. Once again, you do need to actually calculate how many, which one's the limiting reagent. It should not be based off of these numbers. And again, that is very commonly what people will do is they'll look at these number and go, oh, the one with the smallest number of moles is our limiting reagent. And that is not how you determine it. Or they'll look and go, the one with the smallest number of grams perhaps is our limiting reagent. And that is not the case. I will say in a lot of cases it may end up that way, but based on the stoichiometry of the equation, the one actually with the smallest number of moles may be your limiting reagent, but actually the one with more moles could actually end up being your limiting reagent. So it is based on the balanced equation. So you got to actually do a calculation to determine which one's your limiting reagent. It can't just be this guy's got the smaller number of moles, so that's going to be my limiting reagent. Any questions on that? All right. Let's see here. Let's try one here. All right, so with this particular one here, we got this equation. If we react together 6.83 grams of iron with 9.34 grams of sulfur, which is the limiting reagent, and how much iron T sulfide would be formed in this case? How many grams? I'll give you some numbers here that might be helpful. Iron is 5585. And sulfur 3207. And why don't you also calculate how much grams of your excess reagent left over? Okay, let's take a look, see how you're doing. So once again, we have 6.83 grams of iron. We're going to allow kind of to react with 9.34 grams of sulfur. We basically want to know how much product we're going to produce. We also want to know how much of our excess reagents left over. Again, I would say probably in most cases when you come across a stoichiometry problem, they are not going to tell you it's a limiting reagent problem for sure. They're just going to give you the information. So they're just going to tell you pretty much this right here, what's up there. You got like 6.83 grams of iron. You're going to let it react with 9.34 grams of sulfur. You know, how much product are you going to produce? So again, remember that the way you could recognize it is a limiting reagent problem, and you need to kind of figure that out, is based on the information given to you. So hopefully at this point you understand that if you have the grams of iron and you have the grams of sulfur, you can very easily get to moles of each of those. And that's pretty much the key to know that this is a limiting reagent problem, because I have enough information to get to moles of each of our reactants. So again, whichever sort of method you want to choose, I'm going to go with the first method here again, just to show it to you. First two steps are pretty much straightforward for any method you choose. We want an equation and it's balanced, so we're good to go here. So that's balanced. We do want to convert both of our reactants in this case into moles. So I'm going to take my 6.83 grams of iron. I'm going to use the molar mass of iron from the periodic table, 5585 grams per mole of iron. And that will give me for my iron here 6.83 divided by 55.85, about 0.122, I'll call it 3, 2, 3, yep, moles of iron. I'm going to do the same calculation for my other reactant, which is 9.34 grams of sulfur. We're going to once again use the molar mass there from the periodic table to convert it into moles. And 9.34 divided by 3207 going to get me a 0.2912 moles of sulfur. Once again, this is like your starting amount of each of these guys. And again, as you can see there, just from that really second step, We definitely were able to get the moles of each reactant. So again, because of that, that tells you we do have a limiting reagent type problem. So again, in this method, what I'm going to do is I'm going to choose, again, it doesn't matter which one you want to choose. I'm going to choose one reactant, try to figure out how much of the other one I need to use it up. So in this case, I'm going to try to figure out how much sulfur is needed to use up all the iron. And again, this is sort of our limiting reagent sort of calculation here. So to do this, I'm going to start with my iron that I'm starting with, which is 0.1223 moles of it. I am going to go to the equation and find the relationship between iron and sulfur. And from the equation, it is a 1-to-1 relationship. So 1 mole of iron will give me 1 mole of sulfur. And that should mean I need 0.1223 moles of sulfur is needed. And again, that is how much sulfur in this problem is needed to use up all of my iron. First off, any questions so far? Now, what I do with that is I want to compare that number, how much is needed, to how much I'm starting with, which I calculated above. So I'm going to take this number and compare it here. And here I need 0.12 moles. I have 0.29 moles of it. I do have enough. And because I have enough, what that tells me is, in this case, the sulfur is going to be my excess reagent. And by default here, the limiting reagent will be the iron. So whichever one you figure out by comparing how much is needed to how much you start with, the other thing or the other reactant will be the other thing that's happening. So once again, if I were to compare at this point and I did not have enough, then that would tell me sulfur would be my limiting and the other guy would be my excess, and vice versa, obviously. Now that I did that, I know which one's my limiting reagent. And really at this point, I can now just pretty much pick up with the problem I'm really looking forward to answering, which is how much product I'm going to actually produce. Once again, you want to always start here with your limiting reagent, and you want to start with the starting amount of your limiting reagent. So that is going to be 0.1223 moles of iron. I can now do the relationship between my limiting reagent and my product from the equation, and it also is a 1-to-1 relationship. So from the equation, I can see 1 mole of iron will give me 1 mole of my product, and that will give me 0.1223 moles of my product. And by the way, this again would be my theoretical yield in moles. I do want to figure out grams, so I do need to do step number 4, which is take my moles and convert them to grams. So 0.1223 moles of FeS. I do need to calculate the molar mass of FeS, and that's going to be a 5585 plus a 3207 here from the periodic table. That's going to get me 5585 plus 3207. Going to give us an 87.92 grams per mole, which we'll use over here as a conversion factor, 8792 grams per mole. Moles will cancel. And that's going to tell me here in this particular case, I'm going to produce about 10 point, I'll round up. I got a 5 on my calculator there. So 10.8 grams of FeS. This would be my theoretical yield in grams in this case. First off, any question on that there? Now, the additional thing that I wanted you to answer was how much of your excess reagent would be left over. And because I did choose sort of this method, and I picked luckily here, I actually have all that information sitting in front of me. I don't necessarily have to go back and recalculate it. So from my limiting reagent calculation, I figured out I needed 0.12 moles of my excess reagent, and I had 0.29 moles to start with. So the excess leftover would be my starting amount, 0.2912 moles of sulfur, minus what I calculated actually up here, how much was needed, 0.1223 moles needed of sulfur. Will tell me that I got approximately here about 0.1689 moles of sulfur left over. And once again, I can use the molar mass of sulfur here from the periodic table to figure out how many grams that represents. And if I times that by 3207, I got about 5.42 grams of sulfur left over in this case, right? We obviously started with 9 grams of it, right? 9.3 grams. So in this case, we used just under 4 grams in this particular reaction. Yeah. Any questions on that there? If you use the other method, you would have to really go back probably and do this calculation and then do this calculation to figure out how much is left over. So you would probably have to go back, obviously, and do those calculations. Any questions on any of that there? Yeah. All right. Let's try another one here. If you took 622.7 grams of NH3, the molar mass given to you, 1703 grams per mole, and reacted with 1,241 grams of CO2, how much product would you produce in this case? We'll give you the molar mass of that as well, so you don't have to calculate it. How much product would you produce there at 60.06 grams per mole, which is the molar mass? So give it a go, see what you come up with. How you're doing. So once again, we got basically a stoichiometry problem. We got 622.7 grams of NH3. We're going to react that with 1,241 grams of CO2. We want to know how much of our product is produced. So again, like I said before, they usually will not in blinking lights tell you it's like a limiting reagent problem or not. So when we sort of look at this, we do have grams of this reactant. We do have grams of this reactant. Once again, we can very easily get to moles of each of these reactants. And that is the thing that tells you this is a limiting reagent problem. So again, if you can very easily, with the information given to you, get to moles of each reactant, then you know you have to do that sort of limiting reagent sort of step or calculation here. So with that being said, we are just going to kind of roll through our limiting reagent sort of steps and erase half of the numbers there. Maybe not. Let's see here. We'll put our grams back maybe. All right, so first step is balanced equation, which obviously we do have. Second step is we want to convert to moles. So first step done. Second step we do need to do. So we're going to take our 622.7 grams of NH3. They were nice enough in this problem to give you the molar mass of NH3. Once again, if it's not given to you, you need to go to the periodic table and calculate it yourself. We'll use that as a conversion factor here. Again, grams are going to go on the bottom, so we end up with moles up on top. And that's going to give us, starting with for our NH3, 622.7 divided by 1703. We're going to end up with 3656, looks like, moles of NH3. We'll do a similar calculation for our other reactant, 1,241 grams of CO2. They also gave you the molar mass here of CO2. Again, without them giving it to you, you do need to go to periodic table, calculate it yourself. I would say probably most of the time you will need to do that. Divided by 4401, going to give us 28 point, we'll go to moles of CO2. Once again, you can kind of think of these numbers here. Really all you did is just convert units from grams to moles. purpose of that, again, is so we can kind of use it in the right units. But again, we want to think of this as our starting amount, how much we're going to dump in there. So now we know we need to do our limiting reagent. So once again, does not matter which one you choose if you're doing this method. We're going to choose one to figure out how much of it we need to use up the other. So in this case, I will figure out how much we'll do CO2 is needed to use up all the NH3 in this case. So again, this is just a very basic stoichiometry calculation. To figure that out, we will start with our NH3, which we want to use up, the starting amount of it. We will then go to the equation and find the relationship between the two reactants. And in this case, from the equation, it is a 2-to-1 relationship. So for every 2 moles of NH3, which needs to go on the bottom to cancel, we get 1 mole of CO2. The moles of NH3 cancel, and we end up with 3656 divided by 2. We end up with 18.28 moles of CO2 is needed. Once we figure out how much, in this case, CO2 is needed, we again want to come up to our starting amount of CO2, and we want to compare. And in this particular case, we need about 18 moles of it, and we are starting with 28 moles of it. So once again, here we do have enough. And just from that piece of information, that will tell us that this CO2 in this case is our excess reagent. And our limiting reagent here is going to be our NH3. Any questions on that part there? All right, now that we know our limiting reagent, which one it is, and again, the importance of that is, as we talked about earlier, it is always the limiting reagent that determines how much product you make. So when you're trying to figure out how much product to make, you have to use the limiting reagent to do so. Now, you may be asking, what about the earlier problems we did where we didn't have a limiting reagent situation? In those situations where we were figuring out product, it is basically assumed that whatever number they gave you is the limiting reagent and the other one's the excess. So it's sort of an assumption that's sort of made. If you're only given one piece of information about a reactant, it's assumed that that's probably your limiting reagent. So you don't need to figure it out. In this case, you do need to figure it out. So here we want to, again, as I mentioned earlier, make sure that we do go back and continue on with the starting amount of our limiting reagent. So for our third step there, we're going to take our starting amount of our limiting reagent. And now we could actually figure out how much product we would produce. So from our limiting reagent, which is NH2 to our product, our NH3 to our product, that is a 2-to-1 relationship. So for every 2 moles of NH3, we get 1 mole of our product. And again, that's the stoichiometry part. That is coming from the balance equation, the coefficients. The moles of NH3 will cancel, and we will end up with 3656 divided by 2, 18.28 moles of our product. And at this point, we can now figure out the grams of our product using the molar mass, which again, they were nice enough to give to us in this problem. Usually not given to you. You usually got to go to periodic table and calculate it yourself, but we will borrow it here since they did. And again, that is of our product. And we will end up here then with 6006 on that. About 1098 grams of our product in this case. And once again, we might want to look at some sig fig. So it does look like 4 seems to be a very popular sig fig. So we will actually end up with what I got there. It looks like it's actually 4 sig figs. This again would be our theoretical yield in this case. Yeah. Any questions on that? Again, wasn't maybe necessarily asked here, but if I wanted to know how much of my excess reagent is left over, because I actually chose good in this case, I could very much quickly calculate that. Excess left over, we take our excess starting amount, 28.2 moles. We take what we calculated, which is how much we needed. minus 18.28 moles needed. And that would tell us in this particular reaction here, 28.2 minus 18.28, we would have about 9.92 moles of our CO2 left over. And you could times that by 4401 grams per mole to figure out how many grams that would represent. And it would represent about, we'll call it 436.6 grams of CO2 left over. Again, I don't think it was asked for in this case, but again, by doing this method, we actually have the calculation there. And if we did need to know that, we could very easily kind of figure it out. So in this case, we started with about 1,241 grams of CO2. We would have about 437 grams left over at the end of the reaction. And obviously, once again, our limiting reagent will be zero. Basically, at the end of the reaction, it should be pretty much zero as it gets all used up. Any questions on any of those steps there? Question on limiting reagent problems, how to sort of handle them. Yeah. Okay. All right. So the next thing we're going to talk about are yields, which we've sort of been touching upon here as we've been going through these examples. As I scroll through our example we just did. Hopefully they got the same number. That would be good. Hey, they did. What do you know? All right. So let's officially talk about yields of reactions. As I mentioned earlier, when we're talking about a yield is always a product. Yeah, so it's always a product. It's got to be on the right-hand side of the arrow. It's got to be over here, basically. Now, there are a few different types of yields that we sort of come across, and the first yield is what we sort of been seeing, and that is the theoretical yield. And the theoretical yield is the one that's really based on the balance equation, and it's based on how much reactants you're starting with. And that's going to determine, in theory, if everything went perfect, no side reactions, you didn't drop anything, you didn't leave some yellow on your beaker like tomorrow, or on your glass stirring rod, or everywhere else yellow. You will have basically your theoretical yield. It is your maximum amount of yield that you should get in this reaction if everything went perfectly. Now, in reality, as we talked about, things don't go perfectly ever, usually. So we have the actual yield. And the actual yield, much like it sounds like, is actually when you did the experiment, that's how much you got. So at the end of the experiment, that is how much you got. The good news about the actual yield in a book type problem is they usually give you that. So usually they will give you that because you're not doing the experiment. So usually in a book type problem, the actual yield is usually just given to you. Obviously in the lab, like we're doing tomorrow, you will figure out your actual yield from the experiment. But like in book problems, usually it's given to you. So usually the theoretical yield you do need to calculate based on the equation. Now, when you're calculating the theoretical yield, it could be one of two types of stoichiometry problems like we've been talking about. It could be just a basic stoichiometry problem like we did at the beginning, or it could be a limiting reagent sort of stoichiometry problem like we've been doing here towards the end. So one of those ways, you usually will have to calculate the theoretical yield. I would say in very few cases, the theoretical yield is usually given to you in a problem. So you usually have to calculate that. Again, either regular or theoretical, or regular or limiting reagent type problem. Now, what do you do with both of those things? Well, usually your theoretical yield should be higher than your actual yield. You typically will use both of those things to calculate what's known as the percent yield. And the percent yield is the actual yield divided by the theoretical yield. Unlike percent error, where we're trying to have a small percent error, for percent yield, we're actually looking for a bigger number. So percent yield is like how good you kind of did. So if you have a higher percent yield, you did pretty good in that experiment. If you have a low percent yield, you probably dropped stuff all over the place and didn't do it very well as well. This obviously should be a number ideally below 100%. If you get over 100% yield, that for some reason usually means that maybe there's something went wrong there for you. So a very common way, like the experiment, for example, we're doing tomorrow, you're going to basically make a precipitate in a solution which has water and basically and it's wet, right? And you're going to eventually at some point do a little badly drawn filtering here. So you're going to pour your stuff through here. The liquid part's going to go through into a beaker, and you'll be left with, on a piece of filter paper, for example, you'll be left with your solid sitting on the piece of filter paper. Now, that solid that's sitting on the filter paper is still wet. It still has water in it because it came from a solution that had water over it. And probably when you filtered it, you probably squirted some water in it to help it kind of go through or get it out. So if you're impatient and you go weigh that, by the way, at this point, your filter paper also is wet because you filtered it through. You're going to get a very big actual yield because you get all that water weight that shouldn't be there. And you're going to count all that water weight as your solids weight. And you're going to end up with an actual yield that's larger than your theoretical yield. And that's usually not what you want to do. You want to make sure it's nice and dry so that when you reweigh it, the only thing you have is the actual amount of solid that you produce in that case. So that's a very, very common way people end up with a 200% yield or something like that because, it's still wet, it's not fully dried out, and you have a lot of that water weight along the way. So usually if you go over 100% yield, usually indicates maybe not so great. Will you get slightly over in some cases? You will probably, you might get slightly over, but if you're pushing like 110, 120, 130, 140, 200 or 300, 500% yield, you probably did not do things so well. So this is one case where over 100% is not always a great thing. You can't go like, cool, I did 200% better because I had 200% yield. So you usually want your theoretical to be higher than your actual. But again, in certain situations, it does occur, and that's a very common sort of experiment where it can occur. Any questions on that there? All right, I think it's actually a good place. We're going to lay it up there. We don't run out of time for the next.